we are almost at the end of chapter 8. Okay, now let's consider, yeah, when what you mix is not what you get. Okay, until now we assumed that this equilibrium constant of HA and anion equals respectively formal concentration of HA and A minus. Okay, that's true. Maybe in many cases that's true because the dissociation constant of HA is very quite low. But yeah, let's treat this kind of problem rigorously. Okay, by applying mass and charge balance equations. Okay, let's consider a mixture of HA and uh, sodium anion. Okay, yeah. From the mass balance, we can write this equation. F is the formal concentration, and HA, this bracket tate concentration is the equilibrium concentration, yeah, which means that after dissociation, in other words, after equilibrium, the concentration. Yeah? So the mass balance tells that total concentration of HA and A minus, yeah, which is the sum of the formal concentrations, is equals the sum of the equilibrium constants of these equilibrium concentrations of these two species. Okay, and another equation is the charge balance equation, yeah, which is this one. Some of the positive charges is same as the sum of the negative charges. Okay, and from these two equations, you can write the equilibrium constant of HA using formal concentration of HA and proton and hydroxide concentrations. Okay, and likewise you can write the equilibrium concentration for an ion, yeah, which is given by this formal concentration of ion and proton and hydroxide concentrations, and then uh, substituting these two equations into the expression of dissociation constant, yeah, and you get finally this one. Okay, this equation, you know, to obtain this equation, we didn't uh, have any assumption. Okay, so this is a precise equation. Okay, there is no approximation. Okay, and then let's see what will happen if we make an approximation. Yeah? Here is an example. A dilute buffer prepared from a moderately strong acid. Okay, yeah, to pay attention to this one. Moderately strong acid. In other words, the acid, weak acid, but that acid is relatively strong. Okay, not so weak. For example, let's see, let's consider this uric acid of HA, but the pKa is 2.00. Yeah, in other words, Ka is 10 to minus 2. That's not very small. Hmm? That's uh, high enough. Okay, in this case, and what we'll have to do. Okay, yeah, the question is that to calculate pH of 0.01 mole of weak acid HA and 0.01 mole of A minus, but total the volume is 1 liter. Okay, the analytical concentration, in other words, formal concentration of HA is 0.01 molar, and likewise anion formal concentration is also 0.01 molar. Okay, yeah, here is the equilibrium equation, and this one initially 0.01 molar, for both HA and anion. Okay, and then since HA is dissociated into proton and anion, and then let's say proton produced proton concentration is X, and then this equation holds. All right, yeah, the HA decreases a little bit, A minus increases a little bit. Okay, and then we can write this equation, and so far we assume that this produced in proton amount is quite small, yeah, small, much smaller than initial concentration of HA. So comparing 0.01 and X is much smaller, so X could be ignored. All right. In this case here, we remove X here, and then naturally we get this X value, yeah, which is 0.01 molar, right? 0.01 molar, yeah, from our assumption. But since pKa is not pKa is 2, right? So this dissociation, we cannot ignore. Okay, so if we directly solve, yeah, this equation, and then we get X of 0.00414 molar, not 0.01. Okay, you understand? Hmm? So in this case, we cannot ignore the dissociation, of this weak, moderately strong acid. All right. So the final concentration of HA, the equilibrium concentration is 0.00586 molar, and anion concentration is 0.0141 molar. All right. Yeah. And what's the difference? So upon approximation, in that case, proton concentration is 0.01. Wow! And then HA is almost zero. Yeah. So how if we take an assumption that X is quite smaller than this one, and then you have a different answer. All right. So in the case, this equilibrium concentration is not equal to the formal concentration. Okay. Yeah. In acid solution, well, this approximation is all right. Proton concentration is much higher than hydroxide concentration, and HA can be written this way. And in basic solution, hydroxide concentration is much higher than proton concentration. In this case, we can write this equation. All right. Okay, now let's do it with Cold-Seq. Okay. No, I gave you already a lecture for Excel, Microsoft Excel, and one of its functions is Goal-Seek. Yeah? Goal-Seek is a very strong tool for finding answer, for the very complicated equations. Okay, let's try Goal-Seek for this same question. All right, the question is to find the solution pH. Okay, yeah, and we will go we will use this equation, this one. This is exact equation with no assumption. Okay, here you put some numbers for Ka is 0.01, Kw is 10 to minus 14, and F, the HA formal concentration is 0.01. Anion concentration is also 0.01, and then here in cell T4, okay, T4, you write this equation here, right? Equals, and you write this one. And the idea is that change the proton concentration until you find this calculation equals this equilibrium constant. Okay, you don't have to change the proton and hydroxide concentration at the same time, because proton and hydroxide concentration product is equal to Kw. All right. Okay, and to calculate Ka using this equation, you have to have initial value for proton concentration. Now, your textbook uh, have a guess for proton, yeah, which is 0.001 molar. Okay, that's the initial guess, and then you run this Goal-Seek. Your the Excel automatically change this proton concentration little by little until it uh, this value equals Ka. All right. And then finally, although it is not given here in the screen, but finally your Excel gives you answer for proton concentration, which is 0.00414. Okay, that means what? You don't have to solve this equation. In this case, this equation quite simple, but sometimes it is quite complicated. All right. Yeah, this way you can very easily um, calculate, okay, the, the proton concentrations. Yeah, this is the end of chapter 8, and here's the homework problems. I will put the by when you upload your answer. Okay.